Okay, good morning. So let us go through some case studies on solid fuel combustion. Okay, so here these are the case studies we will see today. First one is a thin sheet of paper burning in several angular orientation with respect to the horizontal. Then when there are multiple sheets kept in parallel, vertical sheets kept in parallel, how they burn for different separation distances. The third one will be there will be a say storage of cardboard boxes in a storage facility, and if there is a upward uh, flame spread on that, how the flame height varies with time. We will see that it's experimental thing. Then the ignition of a matchstick, where the energetic portion which actually causes the ignition, that is shown here using a high frames per second video. Then we will see the experimental video of flame spreading over a matchstick array, a single array of matchstick kept at some separation distance, how the flame spreads, we will see that. Then for storing we use a corrugated cardboard. One of the sheet of the cardboard, how it burns in a vertical orientation, we will see that. Finally, we will see the flame, downward flame spread on a PMMA slab, which is thick fuel now. So this is the first case study where you can see there is a paper sheet. The paper thickness TP is about 0.6 mm, which is actually this. So this is thermally thin, and with respect to the horizontal, this sheet is kept at 90 degrees, that is vertical, and 60 degrees and 30 degrees respectively. And you can see the igniter at the bottom, which ignites and the flame actually forms over this and spreads. And how the flame spread happens in a thin sheet, concurrent flame spread, because gravity is acting at vertically downward direction, and when you ignite this, the flame spreads in this direction. The buoyancy driven movement will be vertically upward. So flame also spreads in the vertically upward direction in this 90-degree case. So this is the video which shows that you can see after ignition, flame rapidly spreads, and you can see the vertices which are formed. And since the fuel is thin sheet, as the flame spreads, the fuel is also consumed, and in the gas phase you can see the oscillations because of the entrainment of air. So this is basically 30 centimeter long sheet, and for the flame to consume it or spread over that, it takes about 9.2 seconds. The flame spread velocity will be 3.26 centimeter per second. In the left side, you see the heat release rate with time. You can see heat release rate rapidly increases, reaches the maximum. Then, as the fuel is consumed, it drops rapidly. So this is the concurrent flame spread on a vertically oriented thin fuel. Now, if the fuel is now kept at 60 degrees angle with respect to the horizontal, you can see the characteristics of the flame spread. Now you can see that the flame spreads, but in the bottom there is no much oscillation as you see in the top. The air entrainment in the top portion has a lot of oscillation. The bottom is elongated good flame, you can see. So you can see that the bottom flame is elongated. Small oscillations are there, but when compared to the top side, the oscillations are very less in the bottom. Heat release rate also increases, reaches the maximum and drops, as we saw in the 90-degree case. Now, when compared to the spread rate at the 90-degree case, it took about 9.2 seconds for the 90-degree case. Here it takes little more time, 9.6 seconds. So the average flame spread velocity is about 3.125 centimeter per second. So the flame spread slightly decreases. Now come to the third case where the fuel is kept at 30 degrees oriented with respect to horizontal. Here also the length is 30 centimeter, and you can see the behavior here. Flame spreads gradually, you can see the flame gradually. Here also the bottom, the flame actually completely spreads, but the oscillations are seen in the top portion. As the flame spreads, it actually consumes the fuel. It takes about 11.1 second to spread over 30 centimeter thin sheet and consume it. So, the average flame spread velocity decreases now to 2.7 centimeter per second. The heat release rate also is shown here. Similar trend is there. It is increases, reaches a maximum very fast. Then as the fuel is consumed, it drops rapidly to 0. So, this is about the effect of angular orientation. You can see that the gravity is always in this way, upside down. So, you can see that the acceleration, see the air entertainment which is actually caused, this has two components now, perpendicular to the sheet as well as parallel to the sheet. So, in the case of vertical, there was only the parallel component present due to the buoyancy driven flow. Here there are two components. This is the cause for the reduction in the flame spread rate. Okay. Now, the second case study is on multiple sheets which are kept parallel to each other, vertically oriented. So, here angle is 90 degree with respect to horizontal, vertically oriented sheets, and we are actually igniting at the bottom. So, the flame is ignited at the bottom. You can see that these two sheets basically are kept at a particular separation distance, and similarly second and third sheet also, in this case there are 3 sheets, they are kept at a particular separation distance. Now, n equal to 1 corresponds to only one sheet present. So, there is no question of separation distance. So, you can see that the flame spread rate is about 39 mm per second. I have just put the values here for as a function of separation distance, but there is no separation distance for the single sheet case. When you go to n equal to 2, there are 2 sheets in parallel, okay, the third sheet is not there, but here the separation distance is increased from 5 centimeter, 5 mm, 10 mm, 15 mm and 30 mm, okay, this S is in mm, okay. So, you can see that as the separation distance increases between these 2 sheets, from 5 mm, you record a flame spread rate lower than that in the single sheet case. Then it increases and reaches beyond the value of the single sheet case when the separation distance is about 15 mm, and it almost stays there, not increase much. From between 15 to 30, when you double it, there is not much variation in the flame spread rate for the n equal to 2 case. Now, coming to the n equal to 3, that means there are 3 sheets kept and the separation distance between any 2 sheet is the same, which is S. It is say 5 mm, 10 mm, 15 mm or 30 mm. So, as seen in the n equal to 2 case, you can see that the flame spread velocity is very low at low separation distance and it increases nicely, but again it is below the single sheet case for 10. When you go to 15, it actually exceeds the both the cases, that is single sheet as well as double sheet cases, and records the maximum flame spread rate. So, this is the in the graph for the n equal to 3 case, that is 3 sheets are there burning, and after that when you increase beyond 15, so to 30, it drops to almost same. So, you can, this is 40, this is 42, 44, so not much difference. So, the important point here is based upon the separation distance, the air entrainment in between any 2 sheets causes the variation in the flame. So, the interaction between the sheets are quite obvious at low separation distances, and the interaction or the interference effect vanishes as you increase the separation distance. So, this is a case done with FDS. You can see clearly that this is the oxygen contours. So, oxygen at the ambient is having a mass fraction of 0.23, and in the flame it decreases. So, it say 1 order of magnitude it has decreased. So, this is the flame zone, we can say. In the case of two sheets kept at different separation distances, you can see that the low separation distance of 5 mm case A does not have any oxygen penetration between these two sheets. Only a single flame, the grayscale contours where the black shows the highest temperature and white shows the lowest temperature. So, this is the temperature contour basically. It also shows that a single flame surrounds both the sheets and both sheets burn as a single entity. When you increase the separation distance to say 10, 15 etc., slowly you can see that oxygen slightly penetrates in between the gaps, and the merged flame comes, that is the flame which is occurring over one of the sheet is also interfering with the second flame which is formed over the next sheet. But when the separation distance increase, the interaction reduces, and at 30 you can see that the interaction completely vanishes. So, both oxygen penetration between the two sheets are clear. Similarly, two almost individual flames form, but here the flame spread rate was slightly higher than the single sheet case because there is some heat interaction between these two flames. So, causing that if you increase the separation distance beyond say 30 mm, there will be no significant effect between the two sheet case and the single sheet case. Similarly, for the three sheet case now kept at different separation distance of 5 to 30, you can see that even at the three sheets, the oxygen contours show that, and the temperature contours show that there is no activity between the any two sheets, and a single flame engulfs the three sheets together and burns. When you increase separation distance to say 10 mm and 15 mm, you can see that oxygen tries to penetrate, but not much. Again, a merged flame is seen here. But in this case, you can see that the heat interaction from the neighboring or the outer sheets causes a faster propagation of the inner sheet. Going to the largest separation distance of 30 mm, we can see that penetration is now good between these two sheets, but even there is some lag between the outer and the inner sheets. So, these are the videos which show that this is for basically two sheet cases here, these four, and these four are for the three sheet cases at different separation distances. So, this is for the n equal to 2 separation distance of 5 mm. You can see that a single flame forms and it consumes the sheet. Now, going to the second case, higher separation distance, a group, there is some activity between these two sheets, but obviously you can see that there is a merged flame, that is interference is still there. Going to the third case, you can see that again a merged flame is seen, but there is some lag between these two sheets, that is the left is seen to propagate at a slightly faster rate than the right. When you increase separation distance to 30, you can see that the flames are almost individually burning in two sheets. Now, going to the three sheet case at low separation distance, it is evident that a single merged flame form, and it actually try to burn this together. The second case, similar activity is there. We can see that initially the middle sheet try to burn faster, but after that the initial the outer sheets have burnt and the middle sheet burns like in a slow manner. The third one, separation distance is 15 mm near the three sheets. Again you can see that the merged flame is almost consuming all the 3 sheets at almost the same rate. Coming to the last case of 30, you can see that due to separation distance is higher, individual flames are formed over these sheets, but due to the heat interaction between the outer sheets, we can see that there is a faster burning of the middle sheet. Now this is the vertical fire spread over a cardboard boxes, which are, see, these are cardboard boxes which are kept in a storage facility, and there is a big it's very high, basically about 10-meter high storage, and if there is a fire at the bottom, okay, some accidental fire, how the flame height varies with time is shown here. You can see that the flame is initiated accidentally or wantedly to study how the flame spreads. You can see that initially the flame height is low, and once the ignition is started, radiativity transfer etc. occurs, a exponential increase in the flame height is seen both in experiments as well as in the predictions. So this is how the flame height varies. Concurrent flame initially will be slow, but once it accelerates, it goes at a much faster rate, and the heat release rate also grows. The flame height actually indicates how the heat release rate also will vary, correct? So the heat release rate also grows in this manner. Now this shows a 4000 frames per second high definition video of, so a matchstick. A matchstick, you know that at the tip of the matchstick, so there is a matchstick. At the tip of the matchstick, normally you have a energetic material. When you rub it with some other material, you will have a flame formed, and this flame actually ignites the matchstick, and the matchstick burns basically, correct? So this is the scenario here, but this high speed video shows how the energetic material which is coated over the matchstick burns, okay? So this video will play. Yeah, so it is now ignited with a heat source. This is a heat source which is brought and very carefully ignited locally, okay? It is not ignited by rubbing it with surface, carefully ignited slowly at local point. So once the ignition has occurred, you can see that ignition occurred at local point, then the energy material is consumed. You can see the energy material is coated over the surface, correct? Now as the energy material is slowly burning, because it is 4000 frames per second video, slowly burning, and it is first consuming. Within the time it actually burns, you can see that nothing happens to the wood. The wood here, there is nothing, not even blackening of the wood, correct? So nothing happens, but the wood portion which is coated with this energy material, you can see the char formation, the blackening of this char formation occurs, and slowly the flame is established. This burns first, then due to this heat, it actually causes volatile material to come out of this and forms a flame over this. So that is what is fixed here. It clearly shows that there is a significant time which is required to even ignite the matchstick. So this primary fuel, what I say prime fuel, what we coated, that is very energetic, that actually burns much faster and causes the ignition. Now this is a video which has some matchstick array. It's a single array, that is single row with matchsticks where the energetic material is removed now. That's the same material as the matchstick, what we can say. Now this is kept at almost same separation distance. There will be some small variation, but it is kept at almost same separation distance, and almost same height is projected out of the base, and the first matchstick tip of that is ignited. So let us see how the flame propagates over this. You can see that it is ignited, but the ignition energy is slightly higher, so that two matchsticks are now ignited at the same time. So we will not worry about the first matchstick now. The second matchstick burns now. The flame does not ignite the third one, but it propagates down slowly, ignites the portions below it, but after it ignites about halfway through, the flame spreads over halfway through, it ignites the second or the third matchstick, subsequent matchstick. And again, if you see that after spreading about halfway through, the subsequent matchstick is ignited. So, the flame spread initially is slightly faster. Okay, now you can see that the flame spread from the third to fourth, now it's fifth is ignited. Okay, now we expect this to continue until the entire array is burnt, correct. So, let us see this. Now, you can see that once this is burnt, you can see the red hot zones where the char itself is now burning, and due to the burning, the structure actually slightly bends. The structure of the thing is not actually very erect, it actually bends, and now we can see that the sixth matchstick has ignited the seventh one and it is charring now, and now you can see that after spreading to more than half only, it is igniting the next one. Previously, as it comes to about halfway through down, it was able to ignite the next one. Now you can see that after about 80% spreading in one, then the next one was ignited. So that is now lag. So initially it was faster, now it is slowing down slowly. So you can see that about this side it has come, now it has just ignited this. So that is increasing time delay between the ignition of the neighboring matchstick. So this is because of several aspects. The entrained flow which is occurring from the sides, okay, etc. causes this. But please see this, there is no flow of air from left to right or right to left here. That is aiding the flow flame spread or opposing the flame spread. Only the natural entrainment of air occurs. But you can see that now about 90% is burned, then only the subsequent matchstick is ignited. So as you go, as the flame spreads over these matchsticks, it is causing more and more delay. Now you can see that one of the stick, this is heterogeneous wood sticks. So the burning rate of the wood stick also retards because of some problem in the wood stick itself. So maybe the moisture content may be high and so on. So you can see that it ignites now faster, but after some time you will see that it is now spreading at a much slower rate. If you see the time it has taken to spread over the first 6 sticks, now further some 7 sticks, it has taken much more time, and now it is in this stick, it is not even able to, it is slightly pyrolyzing this stick, but not able to ignite this, and the flame does not spread after this particular point. So this clearly shows that the wood is very extraneous in nature, and any perturbation in the outside flow may prevent the flame to spread. But please see this is separation distance where at least the flame has spread halfway through. If the separation distance is slightly increased, the flame may not even spread from say few sticks also. But if you can reduce the separation distance, obviously the flame will spread through the entire length. So this is about that. Then coming to this, where see the storage box is a cardboard which is basically corrugated paper. So it's a thin paper which is having some pores, etc. So this cardboard, a single cardboard sheet is taken, and in the bottom you can see there is some prime fuel, some small thin layer of liquid fuel. If you ignite this, then this flame will cause ignition of this entire length at one stretch. So when you ignite it, what happens? Concurrent flame spread you will see. So ignition is done. So a flame forms over the entire this. So this experiment is done in WPI. Okay, most of these experiments what we are reporting here is done in WPI, USA. So you can see that the flame is formed and it ignites this. Initially the flame spread is very low because it has to heat up, pyrolysis gases to come out, then it basically sustains a diffusion flame. Now this cardboard is ignited, you can see that the cardboard is burning here, char is formed because it is a charring fuel. Again you see this, there is flame has spread, this is the position. Now after a flame is initiated, due to bioenergy the flame grows at a faster rate. You can see the pyrolysis zone growing at a much faster rate. Now both the sides are burning, you can see the flames from either side, then the flame just accelerates. So you can see that this is very slow initially, but it grows almost exponentially, the flame height or heat release rate with time. So, that is the way the concurrent flame spread is happening over the fuel. So, now the final case study is on the downward flame spread here. So, for example, this is the PMMA slab, which is very thick basically. So, more than 1 inch thick, so 25 mm thick you can say, and this is there are markings we have made here. So, we try to ignite the top portion so that a flame forms, and this is uniformly heated so that the flame forms in the entire length here, and the flame tries to propagate down. So, that is what we are trying to do in this downward flame spread. On thick PMMA slab. So, this is actually thermally also thick. So, when you ignite it, so you understand that ignition is done by a propane torch carefully, so that the first layer is ignited uniformly, so that it is taken over the entire length slowly. It takes some time to ignite it. You can see that flash, one flash is formed, then a sustained flame again is not formed, again now a sustained flame is formed. Okay. So, to ensure the complete formation to the entire length, one more coat of layer, this heating is done, then you can see that now the flame is formed, and after the removal of the pilot flame also, you can see the first layer has caught up uniformly over the entire length, and these two sides here, the two sides are covered with aluminum foil, so that the sides will not burn, only this portion will burn. So, you can see that initially the flame is, because of thick sheet, it has to heat up the entire solid depth. So, it is very slow. Yeah, now we can see that after some time it is now spreading over the spreading down slowly. So, after some time we can see the characteristics we want to see here. You can see the bubbling of this. You can see that it melts, the molten layer is actually bubbling over its boiling point, so that you can see the formation bubble and it burns like this. So, these are the characteristics of this flame, and the slow, very slow, gradually it burns. You can see that the burning forms, and in this case basically there is no, even though it melts, the molten layer does not drip, it actually burns much faster, because the boiling point is slightly lower than the melting point in this case basically. So, it burns nicely. The characteristic you can see this is a non-charring fuel. There may be some impurities which can cause some impurity layer which can burn, but you can see this. So, when the air entrains here, it is slightly blue in color, then after that you can see that the char formation etc. comes, and like a diffusion flame it burns. So, these are the characteristics of the solid fuel burning. So, if you take charring fuel, the char formation is evident. In the case of plastics etc., you can see that the melting and vaporization etc. occurs. Even direct sublimation also can occur in this. So, these are the case studies which we want to discuss. So, I will stop here.